Okay, so I want to go through your reactions lab report with you here. The good news is that they were better in general than the first set. Um, it was very evident that some people were using the resources more effectively than they did the first time around. The bad news is that I only say some people. Here's how I can tell that only some people use the resources available. When I go to my YouTube channel and I look at the number of views for the 2 podcasts related to the lab, 30 views and 36 views. I teach 84 students. Okay, that tells me not everybody is using them. Okay, the unfortunate part of that is that you're really throwing marks away if you don't. Okay, I gave away a bunch of stuff in those podcasts. Okay, in fact, I gave away most of the reactions in the podcast. Okay, the ones that you had to write down, at least the formula form version of them. Okay, in the podcast, which was 5 marks. Okay, in the analysis section, and I still saw on people's lab reports that didn't do well, evidence that 2 things didn't happen. Okay, the 2 things were they didn't listen carefully enough in class or make notes of the things I said to do in class. Okay, and they obviously didn't then take the opportunity to hear those instructions a second time with the podcast. Okay, while they were putting their lab report together, there were just some things on some lab reports, obviously not on everybody's, okay, but on enough that just said I didn't listen. Okay, and I didn't make use of the opportunities and resources afforded to me. Okay, and guys, I mean that's your choice. I can't force you to use it. Okay, but I'd sure like to see you demonstrate to me what you're capable of. Okay, and these are ways for you to do that. Okay, you know, those little tips and hints that just give you the, oh right, I forgot all about that. You know, and then you put it in your lab report like you're supposed to, and you get the marks for it. It's because you know it, but you forget to put it in. Okay, or you forget to do something because you forgot the instructions or just didn't listen carefully enough or whatever. Okay, but that's why they're there, to give you that little reminder so that you can better show me what it is you know. Okay, because unfortunately, guys, in the real world, if you don't show people what you know the first time, they're not going to give you a second chance in a lot of situations. Okay, you got to have it all there the first time. Okay. Okay, so a couple of things on the lab report. Okay, so for the design, we were supposed to identify manipulated, responding, and controlled variables, okay, and explain our choices, okay. Still had a few people not explaining their choices. I don't understand why, but I mean, again, that's your choice. If you're not explaining them, though, the best you can hope for is 2 out of 5, okay, in the design part of this, because the explanation demonstrates to me your understanding. Okay, so what I'm looking for in the design part here, okay, first off, we have to rewrite the problem in our own words, okay, and to be perfectly honest, guys, that's the thing I look at the least, okay, I look to see if there's a question there that has something about what we talked about, and then I'm good with that, okay, so for this, what determines if a chemical reaction will occur? How will an observer know if a reaction has occurred? Something like that, okay. Now, our variables, okay, we said in class that our manipulated variable is the reactants, or are the reactants. Okay? They're the reactants for each test. The explanation is that they will be changed by the experimenter for this reason. Okay? We can't just say they're being changed. They're being changed by the experimenter in order to observe the effects of different combinations and as subjects with different chemical properties. Here's how they're different. Here's why they're being manipulated. Here's how they're being manipulated. Okay? Those 3 things. And it took me like a moderate length sentence. Okay, it wasn't like I had to write a whole paragraph. Okay, I said those 3 things succinctly. All right, we said that our responding variable was going to be the evidence of chemical change. Okay, a lot of people just put results of reactions, which is okay. It's not quite as technical, but okay, evidence of chemical change. That is, and I'm specific here, color change, temperature change, precipitates, or gases evolved. So I'm saying these are the things I'm looking for. This will be different for each manipulated combination as they have different physical properties, and after each reaction will show new physical properties. Okay? That's why we see color changes, precipitates being formed, because the new things formed in a reaction have different physical properties. Maybe they're less soluble, so they form a precipitate. Maybe they're a gas, so they bubble out of the solution. Things like that. Everybody follow there? Okay? So I'm stating specifically, I'm looking for these things. Here's why I'm looking for them. All right, controlled variables. You need 3, and each controlled variable has to be explained. In that explanation, you need to tell me why you're controlling it and what effect it might have. Okay, so first controlled variable, the temperature of the reactants. Okay, temperature affects the rate at which compounds react, as well as other physical properties like solubility. Okay, atmospheric pressure. Gases are released at different rates and behave differently based on atmospheric pressure. Amount of reactants. Amount of reactants can influence the intensity of a reaction. Okay, so here they are. Here's the effect they could have. All of these variables will be the same for all tests, so as to remove their effects from the experiment and eliminate them as a source of error. Okay, everybody follow there. Okay, this part was done much better. This was probably the most improved part on people's lab reports from the first lab. Okay, there's still not much, in some cases, not a lot of explaining going on. Okay, the next part. Okay, in our hypothesis, and I said in class in the podcast that we needed to have the if part talking about what Dalton said happens in a chemical reaction. The and part describes the experiment, and the then part predicts our results and tells what we should be able to do. Okay? So, if a chemical reaction is, and here's Dalton's thing, the separation, joining, and or rearranging of atoms, causing new substances with new physical and chemical properties to be formed. That's what Dalton said. If that's what a chemical reaction is, and various ionic compounds, acids, and bases are combined on a spot plate, then temperature changes, color changes, gases evolved, and precipitates should be observed, as these are all signs that the end products are different from the reactants. Okay? Here's what I'm going to see, and here's what it says. Here's what it will tell me. Okay? I'm going to see the signs of a reaction because they tell me I have something new. Okay? That has to be part of the hypothesis, because now, when I'm done the experiment, and I see that I got color changes, precipitates, and gases, I can say, hey, look, I saw all of those things. Okay? I said that they would be signs something new was formed. I saw them all. Chemical reactions occurred. My hypothesis is good. Okay? At the end. Well, we wouldn't say it that way, but okay, that's where we could go with it. All right? Does everybody follow me there? Okay? I had a better job of putting if, and then in there. Okay? I had a lot less I think hypotheses. Okay? I still had some I think hypotheses, but okay, we got to be if, and then. If this is true and this is done, then this is what's going to happen. Okay? It's always got to run that way. All right, then underneath that we had our predictions, okay, which we did in class, okay, and we're in the podcast, okay. We know that 2 of them were wrong, and that's okay. They were predictions, right? We'll fix them after we do the lab and we see, okay, what our observations really were. All right, then we had our reaction lab observations. Some people's charts were really skimpy, okay, like the observations listed for number 1 were smelled bad. All right, now, I mean, I just can't give you full marks if all you write is smelled bad. Did it smell bad before or after? What did it smell like? Okay, were there bubbles? Like all it said was like smells bad. Okay, and that's just not a thorough grade 10 level type of observation. Okay, we got to say more than that. Right? Prior to mixing, both solutions were clear and odorless. Upon mixing, a strong odor and a slight drop in temperature was observed. No clouding or color changes were noted. Okay? Didn't take me long to write that, but it's far more thorough than smelled bad. Okay, agreed? All right, for pair number 2, prior to mixing, acetic acid was a colorless solution that smelled like vinegar, okay, while sodium hydrogen carbonate was a white fine solid. Upon mixing, a violent bubbling and fizzing ensued with a final product of a colorless solution. If you had more of the baking soda than vinegar, you may have had some baking soda left over, and that might have been in your observations as well. Okay, for pair 3, prior to mixing, both solutions were clear and odorless. Upon mixing, a slight increase in temperature was noted, and a white, cloudy precipitate was formed. Okay, for pair 4, both solutions were colorless prior to mixing. Upon mixing, the color changed to a bright pink color. No other observations were noted. Okay, pair number 5, prior to mixing, the solution was pink and odorless, while the acetic acid was clear and smelled of vinegar. Upon mixing, the color changed back to clear, and a slight fizzing with an increase of 3 degrees Celsius was noted. I noticed, though, however, when we did the lab that the fizzing didn't happen this time. I think it's just because I didn't have the sodium hydroxide quite as strong this time. Okay. For pair number 6, prior to mixing, the potassium nitrate was a clear solution. The lead 2 nitrate was a cloudy solution. Okay. Upon mixing, a bright yellow precipitate formed. No temperature changes or bubbling were observed. Okay. Pair 7, prior to mixing, the hydrogen chloride was a clear, strong-smelling solution, and the zinc was a dull metallic gray solid. Upon mixing, a vigorous bubbling ensued with a slight 1 degree temperature increase. All right. Thorough observations, they said before and after, so there was some comparison. Okay. In the analysis, this is where things went south for a lot of people. The expectation says right here, using words and formulae, write the chemical reaction for each pair that occurred in this activity, except pairs 4 and 5. So when we came back from the lab, recorded in the podcast, I told you in reactions 1 and 2, these 2 gases were formed. Okay, we went over which 2 gases were formed, and I said, okay, now we're going to eliminate those atoms from the reaction. Here's what's left. Now it's a double replacement reaction. Figure out what the products are. Okay, so most people did pretty good on that, but here's the place where people really messed up. They didn't write them in words. Okay, I had just a lot of these reactions written out. Okay, and it does specifically say, using words and formulae, write out the reactions as they occurred. All right, so for pair number 1, okay, we had, the prediction didn't go as we had predicted. So we had NH4Cl reacted with sodium hydroxide. Okay, and we said the gas that was formed was nitrogen trihydride, or ammonia. Okay. That obviously came from here. So I'm going to get rid of 3 of the hydrogens and the nitrogen, which leaves me with hydrogen chloride reacts with sodium hydroxide. That's a double replacement reaction. I swap the metals, and I have my other 2 products, NaCl and HOH. Okay, and it's already balanced. All right, so written out in words, okay, that one looks like this. Sodium hydroxide plus ammonium chloride equals sodium chloride plus ammonia plus water. You may have had sodium chloride plus nitrogen trihydride. You did have to have trihydride. Why? Peter? It's a molecular compound, right? Nitrogen trihydride, or ammonia, is a molecular compound. It starts with a non-metal. Okay, that was probably, other than forgetting Roman numerals on pair 6, the most common mistake was to write that as nitrogen hydride. Okay, forgetting that it was a molecular compound. All right, for our second reaction that did not go the way we had predicted, okay, in class, I set it up like this for you, and I said CH3COOH, that's the acetic acid, is reacting with sodium hydrogen carbonate, NaHCO3, okay, and that we said a gas, in this case carbon dioxide, was formed. That carbon dioxide came from there. Okay, and then I said, all right, there's a weird thing about how this is written. This is really an acid that should be written like this. Okay, and then this is really just this. So it's a double replacement reaction now that's left over. Okay, we swap the metals and we have our new products. So one of our products is water, and the other one is sodium acetate, NaCH3COO. Sodium acetate. Actually, the stuff they put on salt and vinegar chips to make them taste like vinegar. Okay. Everybody follow there? Okay, so written out in words, okay, it looks like this: acetic acid plus sodium hydrogen carbonate equals sodium acetate plus carbon dioxide plus water. Okay, for pair 3, that one went exactly as predicted, right? We had NaOH plus MgCl2, okay, gives us sodium chloride and magnesium hydroxide. Had a few people forgot the brackets on this one. Okay, that was another common mistake, was to forget the brackets around that polyatomic ion. Okay, and then to balance it, obviously we had two sodiums on each side because of the 2 hydroxides here. We had to put a 2 over there, okay, and yeah, so sorry for this. Okay, we had to put a 2 over here, okay, and that gave us 2 sodiums, so we had to go back over here. That made the chlorines balance, and we were good from there. Okay, pair 4 and 5 you didn't have to do. Pair 6, okay, we have potassium iodide, Ki, okay, reacting with lead nitrate, lead 2 nitrate, and that produced lead 2 iodide and potassium nitrate, double replacement reaction. Okay, the big thing here with the balancing, there were 2 nitrates on the reactant side, so we had to put a 2 in front of potassium nitrate over here, and when we did that, we had to bring a 2 back on this side in front of potassium iodide. Okay, another common mistake, forgetting those Roman numerals, okay, on the polyatomic ions. Okay, hydrogen chloride for the last one reacted with zinc, produced zinc chloride and hydrogen. Okay, common mistake, forgetting hydrogen was special. Okay, so just little things like that. Okay, in general, the reaction part of it was done pretty well. It's just, like I said, a lot of people forgot to write the reactions in words. Okay, or I don't think it was this class, but it did happen in a couple of my other classes. I had a bunch of people who wrote same as prediction. Okay, guys, like you were doing this in Google Docs, how much effort would it have taken to copy and paste the reaction from the predictions down to the analysis? Okay, like I gotta say, I was so incredibly unimpressed when I saw that. Okay, that just says I was too lazy to do it, and that just is not the impression you want to make to somebody who's marking your lab. It doesn't look professional. Okay, it doesn't look scientific. Okay, all right. Now, question number 2. I had a lot of people who just didn't do it. I'm not sure why, but it was absent from a bunch of people's analysis. Okay, what we were asked in number 2 was there was a precipitate being formed in both pair 3 and pair 6. Identify the precipitate. Okay, and I just had a bunch of people who said pair 3 and pair 6. Well, we know that. You said that in your observations. Which product in pair 3 and which product in pair 6 is not soluble? So here's pair 3. Those are the 2 products, sodium chloride and magnesium hydroxide. Realistically, I don't even have to go to my solubility chart to answer this one. Last time I checked, salt dissolves in water. Agreed? Okay, sodium chloride dissolves in water. We can confirm, obviously, with our solubility chart, but we're going to find that it was magnesium hydroxide that was the cloudy white precipitate that formed in that reaction. Okay, magnesium is listed in the 2nd row, okay, underneath hydroxide on your solubility chart. Okay, the other one that produced a precipitate was this reaction, bright yellow powder. All right, if I go to my solubility chart, we said all nitrate-containing compounds are essentially soluble, so it's not potassium nitrate. It's got to be lead 2 iodide, and if you look on the iodide column, lead 2 is listed in the 2nd row. Okay, so that was your cloudy yellow precipitate. Okay, and that's what I said here in question number 2. Okay, I wrote out the reactions again, and I said it was a double replacement reaction, and that after checking the solubility chart, it was found that lead 2 iodide was not soluble and was thus the yellow precipitate. Said the same thing for pair 3. Questions on the analysis? All right, and then lastly for the conclusion, okay, always restate your hypothesis. Okay, so all you have to do is copy and paste it. That's all I did, okay, sort of. Okay, in examining chemical reactions, the following signs are indicators of a chemical reaction: temperature change, blah, blah, blah. Okay, presence of these signs indicates the reactants have chemically reacted to form products that are chemically different. Okay, so I reworded my hypothesis. I didn't just copy and paste it, but it's fine. I told you just copy and paste it, so that's kind of what I was looking for. Okay, now I've got to have the justification. And unfortunately, for a lot of hypotheses, the justification was we saw all of the reactions happen, so we were right. Okay, that's just not going to cut it in terms of a good scientific reason, okay, for you to accept your hypothesis, right? So upon examination of the data and observations obtained in this lab, Notably, the presence of color changes, evolution of gases, formation of precipitates, and temperature changes in many of the reactions, this hypothesis can be safely accepted. So I talked about all the things I said would be present if a reaction occurred. I saw them. I'm mentioning that I saw them. Okay? This is because anytime the above indicators were present, the final products had different physical and chemical properties from their starting materials. So I'm saying, here's what those things meant. Here's why I saw that. This is what it tells me. Okay? So I saw what I said I would see, and it allowed me to conclude this. Okay? That's what your explanation should always include. Right? So it should be a couple of sentences after your hypothesis, your restatement. Okay? There should be a couple of sentences explaining, yes, I can do this, no, I can't. Okay? Sources of error, okay, remember we wanted to list things that we couldn't do anything about, or if you thought of something while you're doing the lab, like, man, it would have been a lot easier if we'd have been able to do it this way. Those are the kind of things we want listed there. Okay? So the spot plate used was white. The one I did when I did this lab report was actually a ceramic one, so it was white, and I almost missed the precipitate in pair 3. You guys had a clear one, but I told you we did have that issue where it's transparent. On a black background, some of the color changes were harder to see, so we had to move them from black to white, okay, as the reactions were going on. Okay, that's certainly a source of error. How do we correct that? I'm not really sure how we correct that other than what we did, which is make sure you've got 2 different color backgrounds when you're doing the reactions. Okay. Number 2, very small amounts of reactants were used. Okay, we still had small amounts, obviously way bigger than we used in lab 1, but we still could have used bigger ones. Would have been more fun. Okay, we've got bigger reactions, right? But I mean, there comes a point where it's just not economically viable to use bigger things. Okay, questions on that? All right, since you have your Chromebooks in front of you, you might want to fill in a couple things here for the class discussion, because we're going to go over that right now. Okay, all right. So what evidence do you have that a chemical reaction occurred between each pair of reactants? Okay, basically you can just look at your observations, but we did see color changes, temperature changes, precipitates being formed, gases being evolved. Those are all signs of a chemical change. Okay, did all groups witness the same changes? And basically that's just double check, okay? Double check that your observations are right, which most of you did using the observations I put there, okay? So that question's kind of become moot, okay? Compare your predictions with the actual changes you observed. Obviously, we had 2 that were wrong, okay? We don't necessarily understand in Science 10 why those reactions don't go the way they do, okay? They're just a slightly more complex double replacement reaction than we've gone over. Okay, realistically, you'll do reactions like that in Chem 20 and Chem 30, okay, and you'll have no trouble predicting them once Mr. Reel or Mr. Bacek, okay, or Mr. Hesch, the chemistry masters, teach you more than I can. Okay. All right, you don't necessarily have to write down everything that I said here, just the general stuff, okay? Don't need to copy down what I have up there. Okay, so general message here, guys, because I'm not going to do this every time. Like, I'll go through the lab every single time, obviously with you, like I just did here, but I won't record it every time, okay? The message I'm trying to send to you here is good job on more of you using the resources, okay? More of you having me review them before you handed them in, okay? I had a lot more people, I think it was around 20 or 25 people, okay? Brought their labs in before they were due and had me look them over, okay? And in general, those people did pretty well. But the big thing here is that there's still a lot of people who aren't, okay? And if you're not, then you have to change your expectations then. Okay? If you're not willing to use those resources or put in a little bit of extra time that it takes to use them, then you have to lower the expectations on how well you're going to do. Okay? Because realistically, it's just not going to happen if you don't put in the effort. Okay? The expectations are higher, and so if you're putting in the effort, that effort will be rewarded. Okay? Because not rewarded just because you're doing it, but because it's going to pay off for you. You're going to learn more. You're going to do a better job. Okay? But if you're trying to assemble a lab report in 15 minutes, okay, and you're just throwing things together and writing same as prediction or stuff like that, okay, you can't expect that kind of stuff is going to earn you maybe the marks you were used to getting. Okay? Getting an 80 or a 90 in high school requires a lot more work than it did in junior high. Okay? That's just the nature of the beast. right? And it gets harder as you go along, okay? Believe me, right? I was an 80s, low 90s student in high school, and I went to university, and I got absolutely owned in my first year, okay? Every step, okay? The expectations are higher, okay? The amount of effort you have to put in is greater, okay? I learned that the hard way, but I learned it, okay? And it's tough. That grade 9 to grade 10 jump is also one of those, okay? You're gonna have to put in more effort than you were probably used to. Awesome question. Yes, absolutely. All right. Any other questions on the lab report? Okay, so just sign out of those guys and put them back.